Hi, let's do some more calculus. I can't believe we're on integrals already and we get to work with them every day. It makes me really happy because you know so much. So let's keep going. Let's learn even more. So in here, I wrote a couple things down already, so I can talk about them as you write them down also. It says, given this function, f of t below. So all of these are f of t and all four of these. It says, use f of x, so capital F of x is equal to this. So I rewrote f of t to be 1 to x right here. And then instead of f of t, I filled in whatever my function value of t was. Down here I wrote f of t actually, and then I did it. So I wrote 1 to x, this is where f of t goes. So 1 to x, this is where f of t goes. And notice the variables here. I have an x, I have an x, 1 to x, 1 to x, but in here it's a t squared, a t, and a dt, and dt. And the ones below that, this is f of x. I almost wrote t and then I changed it. This was capital F of x, but this integral is 1 to x squared, t cubed dt. Over here I've got 1 to x squared, 6 squared dt. So this is all just defining these functions in terms of this integral. Not because of any rule or anything, but just because this is given this way. This is just saying this function is defined by this integral, and that's totally okay. So we're going to use what we know about the fundamental theorem of calculus to figure out what f of x are in f prime of x just in terms of x. So what I mean by that is right now I've got a bunch of t's. I want to get those t's out of there. And I can't just switch t's to x's all of a sudden. Don't do that. So what I'm going to do is use the fundamental theorem of calculus. So over here, this business, I'm going to rewrite this. I'm going to add 1 to the exponent, divide by my new exponent. So 4 divided by 2 would be 2. I'm just taking the antiderivative. And if I check myself just to make sure I get the right derivative, 2 times 2 is 4, 4t, yep, I'm good. Over here, I'm going to add 1 to the exponent, divide, okay? And I know that anytime I do this, when I take the antiderivative, I have to do f of b minus f of a, so I'm doing 1 to x. And now I can substitute in. So I can say f of x would be equal to, whenever I do f of b minus f of a, which in this case would be 2x squared minus 1/3 x cubed. That's what I get when I put in x, minus 2 times 1 squared is 2. 1/3 times 1 squared, or 1 cubed, is 1. So for f of x, I get 2x squared minus 1/3 x cubed minus 2 minus 1 would be 1 minus 1. Let me make sure I'm right on this. I was wrong on this. Hold on, let's check. When I put in 1 cubed, I would get 1 times 1/3 would be 1/3. This should be 2 minus 1/3, which would be, this would be like saying 6/3 minus 1/3 would be 5, hold on, 2 minus 1/3, because I put in 1 here, would be like saying 6/3 minus 1/3, right? And so I should get 6/3 is 2, 1/3, I should get this as 5/3. Oh, good. Then if I take the derivative of that, sorry, I kind of glossed over this, f of x, just in terms of x, I have that. Done. I did this part. Take the derivative. What do you get? (4x minus x squared). That's funny. That looks like exactly what I had up here. Interesting. Let's keep going. Let's do this one. So to find f of x in terms of x, if I find f of x in terms of x, what I can do then is I can say, well, what's the antiderivative? The antiderivative of cosine would be just sine, and this is still of t, but I need to evaluate that doing f of b minus f of a from 1 to x. that would be the same thing as sine of x minus sine of 1. Okay, a little bit strange, but do you see how I've got f of x all in terms of x right now? I've got sine of x. Sine of 1 is just some number. I don't know the number because that's not something that I typically evaluate, but it's just some number. So I have f of x in terms of x. If I did f prime of x, so capital F prime of x, the derivative of sine is cosine. The derivative of any number is still 0. That's interesting. Look at that. It matches. So this was just 4t minus t squared, and I got 4x minus x squared. Nice. And this one was cosine of t and cosine of x. Nice. So I could have just flipped the x's. Maybe. Okay, let's do these ones. You can't just flip the x's on these ones. So what this is I have this integral from 1 to x squared of f of t, and I wrote the f of t here, and then I put in what f of t was, which is t cubed. I'm going to do the same thing I did up above, and I'm going to say f of x is equal to, here I'm going to say t to the 4th, and it's got to be 1/4 t to the 4th. I'm going to evaluate this from 1 to x squared. Remember that I do that f of b minus f of a. That's what I normally think about. I'm doing the same thing I'm substituting in x squared. So I'd have 1/4 x squared to the 4th minus, I substitute in 1/4 times 1 to the 4th. This is all equal to f of x, by the way, still. This would be the same thing as 1/4 x to the, when you have an exponent to an exponent, you multiply. We did that. If I found f prime of x, these are the ones that have matched before, the 4x squared minus the 4t minus 2 or t squared. Remember, they matched. But this one, f prime of x would be 8 times 1/4 would be 2 x to the 7th minus 0, or plus 0. Gross. That's not the same thing at all. Or is it? Let's see. Okay, so we've got something else going on here. Something else is at work. Let's do one more. Capital F of x would be equal to, this is the same thing. Remember 6 square root of t is the same thing as 6t to the 1/2. So if you want to take the antiderivative, I add 1 to the exponent. I divide by my new exponent. So in here I've got 6 divided by 3/2. That's the same thing as 6 times 2/3. 6 times 2 is 12, divided by 3 is 4. I'm still evaluating this from 1 to x squared. It looks gross, but that's okay. I'm going to put in 4x squared to the 3/2 power. Looks funny, but that's okay. Again, 4 times 1 to the 3/2 power. So that means f of x, if I simplify this, I would have 4. Remember what I did over here, and I had an exponent raised to an exponent and I multiplied? Same thing over here. 2 times 3/2 would just be 3, so this would be x to the 3rd power. 1 to the 3/2 is 1 cubed, which is just 1, square root of that, which is just 1. Take the derivative. Okay, so you might be really sad right now because 12x squared is definitely not the same thing as 6 squared of t. 2x to the 7 is not the same thing as t cubed. But these ones worked out so nicely, where this was the same thing as this, just with the x substituted. This was the same thing as this. So what's different about them? There's an easier way for both of these. If you turn to the next page, this has a second fundamental theorem of calculus, and it's pretty long. what this is saying is if f is continuous on an open interval I containing a, so this is just a lot of verbiage in here to be saying we have a continuous function at some interval from a to b, and it says, or this says containing a, so it's over some interval, there's a constant a somewhere in there. Then for every x in the interval, if you take the derivative from a to x, so like the first one when we have 1 to x, the derivative is just the thing on the inside. So if this was all f of x, f prime of x is the same as f of x. So you just take the t and you substitute the x. So the ones we did in the very beginning, when we did this, and we had this integral 1 to x, if I wanted to find f prime and just jump to here, it'd be like, oh, the derivative of an integral is the stuff on the inside, and all I have to do is substitute this. That's it. There's actually a pretty easy way down here too. Okay, so f of t is the antiderivative of f of t, lowercase f of t, f prime of t is equal to f of x. So in this case, when I have a to x, so here I'm going to say, if we got all of these f primes from the page before, this says from 177. This is not, by the way. This should be from page 182. The first one we got was f prime of x, capital F prime of x, was equal to 4x minus x squared. So just writing these down from the previous page. This one was cosine of x. This one, though, was 2x to the 7th, so I'm scratching my head a little bit about this one. We'll see in a second. This one also looks weird. It was 12x squared. So let's see what we can do so I don't have to go through this very long process every time. In this one, if I'm finding capital F of x and I'm on its integral from 1 to x, because this is 1 to x, up here when this is 1, this is any constant that I can think of, so 1 is a constant, to x, this one is, all I have to do is say capital F prime of x, the derivative of the integral, is the stuff on the inside, and I can switch it automatically to x. Same thing here. Take the derivative. The derivative of an integral is the stuff on the inside, but I'm going to substitute this. In both of these problems, there was one more thing we were doing, actually, that I didn't say it out loud. But x is a function. What is the derivative of that function? 1. So if I am taking the derivative with respect to x, you know how normally we don't write dx down, like we don't have to do that every time? This is that same kind of idea. If I'm substituting x, I'm actually putting a function within a function. Wow. Are you so excited? Down here, the reason why these answers are different is because we have to actually do the chain rule. Crazy, right? So when I take the derivative of this function, I take the derivative of the outside. So you see the outside, the derivative of this entire integral would be this, right? The derivative. If I took the derivative here, I would get that this was 3 times something squared. So think about this, this would be like 3t squared, right? But do you remember how we always talked about how we leave the inside alone? The inside's going to look a little funny because instead of substituting in x this time, we're going to substitute in x squared. So we took the derivative of the outside, so this was 3 times something squared. Leave the inside alone. So here, what am I doing with my life? Pause. Okay, so this one, I made a mistake at first, but I'm going to cut that out. It's fine. This one, okay, so this one we get to actually apply the chain rule. We take the derivative of the outside. So normally we would say like 3t squared or something like that, but do you know how this is already an integral? And in all these cases, the derivative was the thing on the inside, right? So this is the derivative. Something cubed is the derivative. But in this particular problem, we're using the chain rule. Wow. When we say we leave the inside alone, all we're doing is putting this x squared in here. Times, in these ones we didn't have to do anything because the derivative of x was just 1. But in this one, the derivative of x squared is 2x. X squared to the third power, you multiply these, so that would be x to the sixth times 2x. Ta-da! Okay, so in one like this, when we're taking the derivative, we're taking the derivative of the outside, which the derivative of an integral is this something cubed, so something cubed. When we leave the inside alone, what we're really doing is putting that x squared in here because that's the thing we're substituting, times the derivative of the inside. That's where this is coming from. Now they match, and it's a lot easier than that way on the front. Let's do it in the next one. So if I want the derivative of f prime, I take the derivative of the outside, which is just the stuff inside the integral. 6 square root of something. When I leave the inside alone, this business, I just write it exactly like it is. Times the derivative of the inside. This is my inside. The x squared is my inside. 6, the square root of x squared is just x. Ta-da! Okay, let's use it a little bit. So, if I'm going to go on to page 184, and I think actually this is the last one I'm going to do for today. So 182 to 184. Given to the right is the graph of f of t. Okay, so this is the graph of f of t, which consists of 3 line segments, 1 semicircle, so that's nice, it tells me that. Let the function g of x define like this. Okay, so we've got some work here. So if this, find g of -6. So I'm going to write in g of -6, and then I'm going to use the function exactly as given, even though it looks funny because it's given it as an integral. I'm going to do this integral from -1 to -6 f of t dt. Now let's think of how to do this one. Well, I have this integral, f of t and f of t matches. So to find the value of that integral, I do the area under the curve. This is from -1 to -6. You're like, that doesn't quite make sense. So we're using properties of integrals, and we're switching it. But when we do, when you switch the limit of integration, you need to switch the, to make this a negative. Okay, so now I have negative, and then whatever my area is. I'm going to go from -6 to -1. To do that, draw a horizontal line from -6 to -1. I'm going to go up at -6, down here, -1. And then I find the area under the curve. So up here, it's a triangle. I can say 1/2 my base. Oh, this is gross. Do you see this? Not cool. I need to find out what this value is. Do I know what the slope is? This is the slope of 1, 2, 3 over 2. So right now I know this is y equals -3/2 x. If I keep going, 1, 2, 3 over 2 minus 5. So I wrote the equation of that line because I want to know what is this function value when y is 0. Where is this line even at? Like, where is this crossing? I can't say -3.5. It doesn't really even look like that. Let's see though. Add 5 to both sides. Multiply both sides by, 5 times -2/3. That would give me -10/3 is equal to the value of x. So right there, I've got x is equal to -10/3. Like, that's the point when y is 0. So the way that that's going to help me is because my base then, this would be negative 10/3 is like negative 3 1/3. So here that'd be 2/3. 1, 2, 2/3. 1 plus 1, or 2 2/3 is the same thing as 8/3. Whew. 1/2 base. My height, thankfully, is just at 4. So I did this. The next part is an area under the axis, and again, I've got to deal with that guy. I can see that this is a trapezoid, but be careful in this one. Do you see how the bases are like that? I may even say, you know what? I know this is a rectangle and here's a triangle. Split it up into that so I don't even have to deal with which ones are the bases. This would have, I'm going to say -2 for the area of the rectangle, minus, I'm going to run out of room, 1/2. The base of this triangle would be 1 1/3 this time. 1 1/3 would be 4/3. The height, I don't have to make it negative because I already did, like I already said, minus this. The height would be 2. And I realize now I have an extra parenthesis for no reason. Whew, this is a lot of work. Okay, this would be 2 16/3, because I did 4 divided by 2 times 8, 16/3, minus 2. So I'm actually going to put this in terms of thirds again. So -2, I'm going to rewrite that as 6/3. 1/2 times 2 would just be 1. So this is just -4/3. So many fractions. 16/3 minus 6/3 would be 10/3, minus 4/3 would be 6/3. So 10/3, 6/3, which is just, oh my goodness, this was a whole lot of work to get. -2. Did you get that also? That was so much work. Okay, don't lose the forest through the trees. You know, this was a lot of work with fractions. Let's think about what we did. Let's go back. We did this integral from -1 to 6 because we substituted in anywhere we saw an x, we put in a -6. F of t matched f of t, so we found the area under the curve. Anything above the x-axis is positive, anything below is negative. But we had to remember at the end we switched the limits of integration, so we made our answer negative. So much work. Let's do another one. If we want to find g of 6, we do the same thing as we did the first time when we substitute x is 6. These still match. F of t matches f of t. So I'm going to go from 1 to 6, drawing a horizontal line. Down on the left, up on the right. And I'm going to break this up into parts to find the area. There's nothing I need to switch here, but I can see this is a -2 rectangle below this. Then I have a triangle still below the x-axis, but I can see, you see this larger square that it's a part of is 1, 2, 3, 4 area. So this would be, you could still do 1/2 base times height, but you would just find that this area is half of that larger square it's in. So I'm going to say -2. Plus, over here I've got 1/4 of a circle. How do you find the area of a circle? 1/4, or you find it pi r squared. This is only 1/4 of it. The radius of the circle is 2. Okay, then I would have -4 plus 4 divided by 4, or 4 times 1/4 is 1. And I should say this is equal to g of 6. This one was equal to g of -6. Hold on, did I miss something here? Because my old me says that this is -8 plus pi. Oh my goodness, do you see what I did here? Guys, this is from -1 to x. No problem. I'm just going to keep going over this whole way. So I have 1, 2, 3, 4 more to add to that, and it's below the x-axis. There we go. That's why you have to check yourself, just in case you wrecked yourself. and then fix it. That's a common phrase. Okay, couple more. This one says g prime of 6. Don't find g prime of 6 until you find what g prime of x is. G prime of x, remember g of x is given by this integral, -1 to x. If I'm doing the derivative of an integral, remember it's just the stuff on the inside with this substituted. If this happened to be an x squared or something like that, you would still have to substitute, so you get x squared, but you'd have to multiply it because of the chain rule, wow, times 2x. This we're technically still multiplying by 1. So we've got g prime of x equal to f of x. G prime of x, if that's equal to f of x, that means that g prime of 6 is just the function value at 6. So I go up to the graph, my function value at 6 is 2. Easy peasy lemon squeezy. G prime of 2 then means this would be my function value at 2. The function value at 2 is -2. Now let's keep going. So g double prime of 2. Before I find that, I'm going to do g double prime of x. Same thing over here. G double prime of -4, I need to first find g double prime of x. So g double prime of x, if g prime of x was equal to f of x, g double prime would be equal to f prime. So in this one I would get g double prime of 2 is equal to f prime of 2. Same thing over here, g double prime of -4 is equal to f prime of -4. Remember what f prime is? F prime is the derivative. The derivative is also known as the slope of the tangent. So if I have the graph of f and I want f prime, I'm finding the slope of the tangent. F prime of 2, ooh, what's the slope right there? It's really hard to see because I wrote over it 50 times, but not 50, that's exaggerating. Ah, it's a sharp turn. Derivatives don't exist at sharp turns. And I would say as f of x, or you can say f of t, it doesn't matter because we've determined that it's the same. You could just say f if you wanted to, at x equals 2. Let's try over here. G double prime of -4, f prime of -4. The slope at -4, this was just a line. And this is nice, we already did some work. This is really giving a reason for my answer already, but because I know the slope of the tangent, this is the slope of f at x equals -4. It's like double reasons. Okay, deep breath. Thanks for working, thanks for learning. I appreciate you. Please let me know if you need anything at all, and I would be happy to help you. Thanks, bye.